computer. Okay, so in theory, I am streaming live, recording, and talking to you in person. So hopefully that is true. Let me go ahead and can somebody wave on the online there? So we'll see. Okay, there we go. Great, I'm online too. Great. So I'm going to minimize this so I don't have to worry about that. So what we're going to do here is we're going to kind of pick up where we left off. First of all, thank you for coming. Obviously, you know, masks are working. My daughter got COVID doing a presentation. She was in theater. Nobody in my family got it because we all wore, we threw her in a room, didn't let her out, all wore masks. We've all tested negative now, so everything's great. So trust the science. That's what we do here. Okay, anyway, so beyond that, we're back here. If you are live or missing this, go ahead and, you know, this video will be online as well on my YouTube channel. Again, if you miss anything, feel free. If you get Bobcat traced and you need to be offline, not in person, please follow the protocols. If you need to catch up, if you don't understand the topic, that's fine. I will be releasing my how to do the homework video this week. So you'll how to attack it, how to look for different information given in those videos. And that's what we'll see when you go to those extra problem solving things. And then I'll also do a thing with the quiz where I'll go through and work through all the problems in the quiz as well. So that way you'll get an idea of how I want you to think about chemistry, because it's all about taking the information you have and making a logical guess. It's not a black box, it's not magic, it's not anything that you cannot do. You just have to look at it in a slightly different way. Okay, so that's the important part. Okay, so where we were last talking about, we were talking about hybridization, okay? And how hybridization means that you can bond different ways. sp3 lets you bond 4 times, okay? So you bond 4 times because you have the s orbital mixed with 3 p orbitals, 4 equal orbitals, it's tetrahedral. You have 4 zones of electronic density. Now, what does that mean about the molecule? Well, the molecule means that if it has 4 bonds, the molecule is tetrahedral. If the molecule has 3 bonds, it is this trigonal pyramidal. And if the molecule has 2 bonds, but still has that tetrahedral electronic structure, it's bent. Okay, so hybridization equals shape, shape equals hybridization. Write that down. Uh-oh. Why? Come on. Go, and I need to change to never sleep. That's what I haven't done yet. There we go. All right, mirroring. There we go. So there we go, and there we go. Okay, so what we're going to see is that hybridization equals shape, shape equals hybridization. So how does that go forward when what we're looking at? Well, we saw that methane had 4 equal bonds because it shared 1 s with 3 p's to give us 4 equal bonds, and that gave us a tetrahedral molecular shape. And that's designated by the 109.5 degrees that we have. Now, we can look at ammonia, which only has 3 bonds. But remember, nitrogen is group 5A, meaning it brought 5 electrons in. It has 5 valence electrons. It needs 3 more to make an octet. So it only has to bond 3 times. So it bonds 3 times and leaves a lone pair by itself. That nitrogen is sp3 hybridized, okay, which means it has 4 electronic zones that are 109 degrees apart. Okay, so these 4 equal zones that are 109 degrees apart, this one has a lone pair. Lone pair is slightly bigger, so it pushes them down a little bit. And so we actually end up with this 107 degree bend we see on the system. And we see that this lone pair takes up a little more room. So it actually pushes them down a little bit and gives it that 107. But it's still sp3 hybridized. It has 4 equal electronic zones. Okay, water is sp3 hybridized. It has 4 electronic zones, but oxygen brings 6 electrons to the valences, 6 valence electrons. What does that mean? It means it only needs 2 more electrons to fill its octet, therefore it only needs to bond twice. So it has to make 2 bonds and have those other 6 electrons fill up those orbitals. So we see that we get the empty or the 2 lone pairs are actually bigger than the hydrogens and therefore squeezes those hydrogens together. Notice that gets even smaller from 109.5 degrees in tetrahedral to 107 degrees in trigonal pyramidal, 3 bonds in a pyramid, to this 105 degrees in bent. But again, oxygen, carbon, and nitrogen are all sp3 hybridized. So that leads to the electronic shape, which leads to the molecular shape. Okay, we get that. That's important. Okay, so when we move on from that, if we don't have that, we can have different shapes. If we only have 3 electrons in our outer shell, boron is in group 3A. It only has 3 electrons. It's one of those ones that breaks the octet rule. If we're breaking the octet rule, that means that boron only needs to bond 3 times to fill its 6 electrons. Okay, 3 electronic zones, trigonal planar. 3 electronic zones, trigonal planar. That means that we have 3 bonds and they're all forming a plane, a little triangular shaped plane. Okay, we're going to see that form again, that triangular shaped plane again. Okay, so don't not remember that. But 120 degrees is as far as we can spread those bonds out in any one in 3-dimensional space. So that 120 degrees tells us that we have a trigonal planar system. Okay, now we do have also beryllium. Beryllium's right here in group 2A, meaning it has 2 valence electrons. But notice it's also a 2s. It's got 1 electron in the 2s. It's got 2 electrons in that 2s. It has a filled orbital. That's why it only needs 2 electrons to fill its orbital. And when it does that, it gives a total of this linear shape. It has 2 electrons to share. It shares those 2 electrons for a total of 4 electrons. Again, it breaks the octet rule, but it gives us a linear molecule, 180 degrees apart. Okay, now we can actually do this with other hybridizations. For example, let's look at this carbon here. What hybridization do we have in this carbon just from the shape? Do we have an sp3, which is 4 equal bonds? Do we have an sp2, which is 3 equal bonds? Or do we have an sp, which is 2 equal bonds? Sp, because number 1, it's linear, right? Giving us the linear shape. So we know it's sp, but what does sp mean? We have 2 bonds that are sigma bonds. The hybridized bonds are the ones that do sigma bonds, okay? But what else do we have? We have sp, but what happened to those 2 other p's? They're unhybridized, making them available for p orbitals or pi orbitals. Okay, so that means there's 2 pi orbitals on this oxygen, 1 going up and down, and then 1 going in the opposite axis here and here. Those 2 unhybridized p orbitals, one of them's bonding to the oxygen on one side with a pi bond, and one's bonding to the other oxygen with a pi bond. So let's look at that carbon again. What's the hybridization on carbon? sp. It has 2 unhybridized p orbitals, meaning it has to bind twice by an overlap bond or a pi bond, okay? So it's very important that we track how many bonds are hybridized and how many bonds aren't. The hybridized bonds make sigma bonds. The unhybridized p's make pi bonds, okay? So what does that mean about the hybridization on oxygen here? How many p orbitals must it have to bond to carbon? The oxygen is hybridized as sp2. Do we see why? There's one p orbital that's making a pi bond with carbon on one side. The other oxygen is doing the exact same thing. That means that there are 3 electronic zones. If we look at there, and our 3 electronic zones are the sigma bond here, this lone pair here, and this lone pair here. Those green regions are 120 degrees apart. And that means we have to have a unhybridized p orbital here to overlap with that carbon. So that carbon is sp2 hybridized with 3 electronic zones, making that the oxygen is sp2 hybridized with 3 electronic zones, making all 3 of those green lobes 120 degrees apart, and giving us 1 p orbital to allow us to do our pi bond. Questions on that? So see how looking at the shape tells you how many hybridized orbitals you have. Hybridized orbitals equal sigma bond. Every unhybridized p equals an opportunity for a pi bond. Okay, questions on that? Okay, we're going to see a lot of that, okay? So that is all we have for the hybridizations. And when we go to SP, we're going to see linear and tube pi bonds. SP2, we're going to see trigonal planar with a pi bond. SP3, 4 sigma bonds, okay? Look for that and understand shape equals hybridization, hybridization equals shape. Questions on chapter 1? Okay, let me, actually I have something in the chat. Yes, okay. Okay, so that being said, let's move on to chapter 2. Okay, so now we're going to have something new to do in the class. Now that we're here, I want to make sure that number 1, you get credit for being here. So if you're on Zoom, I can see you as the Zoom participants. That's fine. If you're here in class, what we're going to do is we're going to remove the chat here. Remove the chat here. What you're going to do is you're going to take out your phone and you're going to hit this QR code. It's going to say a question. The question is, what seat are you in? Okay, so let me show you that. This first row is row A. B, C, D, E, F. That last row there is H. Notice the end of the other row opposite yours should be the same. And then the seats are numbered. 1, 2, 5, 6. The seats are numbered on the front of the seat. Okay. So what this does, number 1, is it tells me you were here. Number 2, it tells me you can locate yourself in a room with 3-dimensional space. Number 3, it'll tell me if you're sitting in the back row and I have to wave really far to see you. Hi. Okay. So if you must be logged into the web, you must be logged into the campus with your net ID. It will automatically populate it for your name, location, not location, sorry, your name and time you logged in. And then it just basically goes to a Google form and I just have it for the future. Yes.
If I don't have a smartphone, is there a link that I could access?
If you can take it, can you take it, touch it with your computer?
I don't know how to scan a QR with a computer.
Okay. What you do is you email me and give me your seat number.
Okay.
Yeah. Sometimes if you have a broken camera or whatever, just email me your seat number during class, preferably, so I'll have a record of it, and that'll do it. So this does those 2 things, you know, make sure that we have our Bobcat track, make sure you get credit for coming. Okay, questions?
You said there was a letter.
Yeah, the first row here is letter A, see the bottom, there's a little thing at the bottom of the row, if you're on the same level, those are the same. I think that's G way back there, those 2 seats, and that's H over there. So, and then 1, 2, I think they're numbered from this side over. But it is on the front of your seat if you have to stand up and look at it. Okay. So that being said, that gives us our way to do our Bobcat track. We're kind of crammed in here, so okay, we'll get the best of it here. Okay, so chapter 2, we're going to learn some stuff here. We're not going to learn exactly nomenclature. We're going to start to see the beginnings of nomenclature, which means naming things. But I want to introduce a bunch of different classes of compounds because the different atoms available and how they're bonded define the classes, and that will define our molecular properties. What kind of bonding it does, whether it dissolves in other things or not, all these other things. Those are kind of things that will happen in there. Let's see. All right. If you're not in the audience, you don't have to use the QR code. It'll be in the who's who. Okay. Okay. So that's being said, let's go ahead and talk about functional groups. Now, why do we care about functional groups? Well, functional groups are the fun part. That's what we get to go from one to the other, none out of the one. So we have to start talking about them as what they can and cannot do. So the first class we want to talk about is hydrocarbons. So that's the simplest class. It only has carbon and hydrogen, right? Carbon is carbonaceous, things with carbon in them. Most of the time they have a hydrogen bond to be considered an organic molecule, okay? So our simplest class is what we call our hydrocarbon class, only containing hydrogens and carbons. Okay, that being said, the simplest class also is where all the carbons are sp3 hybridized. And we call these alkanes, right here, alkanes, all sp3 hybridized. So all sigma bonds, all sp3 hybridized carbons. Okay. So what that means is if we were to draw out a structure using that skeletal form, right, they would all look like basically just sticks in all sorts of weird different directions here. Okay. So what this is telling us is that the sticks obviously are the bonds between carbons. In every unoccupied space up to 4 bonds is going to be a hydrogen, right? So any of our hydrocarbons are the simple sp3 hybridized system. So let's define a couple real quick. So like simple ones that, like if we had 5 carbons, so we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, this would be pentane. It would have 5 carbons and it would have that ANE. This ANE at the end tells us that we only have sigma bonds. Okay, we're going to get into this again in chapter 4, but that ANE means we only have sigma bonds. So what if we have an sp2 hybridized carbon next to an sp2 hybridized carbon? Well, they're going to pi bond, right? So we're going to have not only single sigma bonds, but we're going to have at least 1 pi bond in our compound. If we have at least 1 pi compound in the pi bond in our compound, it changes the name because it has a different reactivity. So this is one. So in the case of this, we have 1 pi bond. At least 1. It can have more than 1. So in that case, we're going to go from this pentane, ANE, saying it has no double bonds, to 1, 2, 3, 4, 5. 1 double bond somewhere in the compound changes it into an alkene, ENE. So ANE means sigma bonds only. ENE means at least 1 pi bond. You can have more. You can have 2 pi bonds or 3 or 20. It doesn't matter. At least 1. Okay, so then if you have a triple bond, which is sp hybridized, let me see, this is sp2 hybridized, which makes these 2 pi bonds between the same 2 carbons. We have sp hybridized. And that looks like 1, 2, 3 there. I'll just draw the carbons there. So the idea here is that our names change with hybridization. Our shape changes with hybridization. So it's easy to follow what's happening. We just need to know that all three of those components are linked together. sp3 hybridized, only carbon hydrogens. It's a hydrocarbon, only sigma bonds. Alkane, at least one double bond between two carbons, alkene. At least one triple bond between two carbons, alkyne, Y-N-E, alkyne, alkane. So A and E has a different hybridization than E and E, which has a different hybridization than Y and E, okay? So be sure to link all three of those things in your head together. It makes it a lot easier when you've never heard of a compound before. You can look at the end of the word and say, oh, it's got to have this hybridization in some way. Questions on that? Okay, any questions in the chat? Nope. All right. So, and I am recording, right? I thought I started recording. Yes. Okay, so let's move on to the next thing. So, after we start with those hydrocarbons, the alkanes, alkenes, and alkynes, the next thing we have is another set of hydrocarbons, which is only hydrogen and carbon, but they have different molecular properties. And we're really going to talk about this mostly next semester. There's an entire chapter on this, actually two, but there's 2 chapters on this in the next semester. But I want to introduce this concept because we're going to use them in a couple different ways. So the one way we're going to use them is we're going to use it as a side group for right now, but eventually we're going to see some cool chemistry associated with them. So the first thing I want to talk about is the special kind, which is the simplest of is what we call benzene. 6 carbons, 6 hydrogens. Now you're looking at that going, well, obviously that's an alkene, right? Because it's got at least one double bond in it. Yes, but aromatic compounds are signified by having alternating single and double bonds in a ring. They have to meet 2 other conditions, but anytime you see alternating single and double bonds in a ring, the idea here is that it's going to have those double bonds moving all the way around that ring all the time. And because of this, we can have what we call it aromatic compounds. Now, turns out these compounds, when they were first discovering them, had weird smells. And so they were aromatic compared to other things. And so that's why we have the name aromatic. But it turns out to be also related to resonance. Remember when we talked about resonance structures, where the only thing that moves are electrons, no atoms move, we didn't break any sigma bonds, all we did was move electrons? Well, in the case of this compound here, because our p orbitals are all lined up together, there's no difference between having your pi orbital here, I mean, your pi bond here or your pi bond there. And as a result, they flip back and forth, back and forth. So it really isn't single bond, double bond, single bond, double bond. What it is now is a whole bunch of half single bonds, half double bonds, all in a ring. That's the distinguishing feature because of resonance, okay? And not only is resonance in play here, that resonance saves so much energy, we actually have what we call resonance stability, meaning that those aromatic compounds don't react like alkenes anymore, they react differently. So that's why they're their separate hydrocarbon group. Now, by adding different things to the ring, like an OH or a benzoic acid here, it'll change the names and properties. But the basic idea here is we're looking at these aromatic compounds have alternating single and double bonds and are sharing those single and double bonds through resonance to give them a different property and therefore a different class of compounds. All right, questions on that? Okay, so those are our hydrocarbons, right? So we have alkanes, alkenes, alkynes, and aromatics. Okay, so let's talk a little bit about what makes hydrocarbons so, in comparison to other functional groups, boring. And we're going to say that by the idea of bond polarity. Okay, we talked about electronegativity when we talked about bonds, right? If the electronegativity was too large, they became ionic bonds. If the electronegativity was in a certain range, we got covalent bonds. But remember, if they were really close together, we had what were called non-polar covalent bonds. In the case of non-polar covalent bonds, our difference is less than 0.5 units. Well, there's no units. 0.5 electronegativity between the two different atoms. Okay, that is a distinguishing feature with hydrocarbons. Carbon-carbon bond is non-polar because they're both 2.5. The carbon-hydrogen bond is non-polar because hydrogen is 2.1 to 2.2 and carbon is 2.5. So those are non-polar bonds, right? So the carbon-carbon bond's non-polar, the carbon-hydrogen bond's non-polar. So there's not a lot of things we can do with it, okay? But if that polarity gets above 0.5, that difference in polarity, difference in electronegativity between the carbon and whatever feature there is, that means we have a polar bond. That polar bond does three things. Number one, it lets you know that there is a reactivity difference between the two atoms. One is going to be slightly positive, one's going to be slightly negative because they have an unequal share of electrons because it's a polar bond. Number two, there's going to be a net dipole. There's going to be some external field created from this, meaning that things with a polar bond are more likely to dissolve in things with a polar bond. So it's going to affect solubility. And it's going to affect where we see things attack, how it's going to react, which side of the bond it's going to be. So we want to look at those three things. So electronegativity tells us a lot about the nature of the bond, but then it also tells us where to look for reactivity, Okay, so with that, let's look at bond polarity, okay? So I said carbon-carbon bonds and carbon-hydrogen bonds should have no polarity, right? Because we have a carbon here and a carbon here, and let's just put some hydrogens on there. Okay. Because there's very little or no electronegativity difference between any of these electrons, these two, remember, two electrons are in every sigma bond here. That's one sigma bond. Those two electrons are evenly shared between those two carbons. Evenly shared between the two carbons. Nice, happy covalent bond. Good roommate. Think good roommate, right? Now, in that case, there is very little reactivity here because they're evenly shared. There's no partial charges. There's no polarity. There's nothing attracting it to the molecule next to it. Okay, so what if we change that? What if we change that so that there is a difference between them? So let's do something like carbon and fluorine, okay? And let's put a couple hydrogens. Let's fill this valence here. So we have a total of 3 bonds to carbon, okay? The difference in electronegativity between fluorine, which is 4, and carbon, which is 2.5, is 1.5, right? So it's not above 2, so it's not ion. It's a covalent bond, but it is above 0.5 in difference, meaning it's a polar covalent bond. What does that mean? Fluorine is more electronegative than carbon. What does that mean? It wants the electrons more. It's pulling electrons toward the fluorine. Let me emphasize that. It's pulling electrons toward the fluorine. What does that mean? That means that the carbon side is partially positive, delta, little delta positive, partially positive, and the fluorine is partially negative. It's all about the electronegativity. Still a covalent bond. It's still sp3 hybridized because it's got 4 equal sigma bonds, but we have a polar bond now. If you looked at that hydrocarbon next to it and the one with the fluorine on it, which do you think is going to be more reactive? you have something that you can attack with a positive or negative charge, depending on which side you want. It's going to react more. You're going to see more chemistry there, okay? So when we look at our systems here, we want to think about, number one, is the bond polar or not, okay? We can decide that by looking at the electronegativity. If there is a polar bond, we need to put an arrow next to it saying that it is polar. It's going in one direction, and to make sure we know that the electrons are going in that direction, we're going to put a little cross on this side of the thing, saying that's the positive side of the arrow. Okay, so that means whenever we have that direction, the positive side is the atom with the lower electronegativity. The arrow points to the atom with the higher electronegativity. Okay, if we do this always, then we can actually say, oh, that bond's polar. But what else is it going to tell us? That molecule might be polar if we add up all of those polar bonds to see where it goes. Okay, questions on that? So, yes.
Like I know that it goes like this,
Yeah.
but like
Most of the time, what we'll deal with is polar covalent bonds, so you'll know they'll be in there somewhere. And except for the couple that are right next to each other, like nitrogen, carbon, and hydrogen, those tend to be fairly non-polar bonds. Carbon with almost everything else is some kind of polar bond.
And we talk about 0.5 being the cutoff. If
Yeah.
you're right on 0.5 is the difference between electronegativity, would that be polar or non?
It's below 0.5 is non-polar, 0.5 to 2 is polar. So that is, there's a less than symbol, I believe, on the table. So the question is, how do we know where our electronegativities, where they are? You can look at the table. Again, if they're right next to each other, carbon, nitrogen, that's going to be a non-polar bond. Carbon, hydrogen, that's a non-polar bond. Carbon with almost any other thing, one atom away or more, is a polar bond until you get up to the ionics. And actually, if you think about it, we're going to end up with going to magnesium here. That actually makes a polar covalent bond. Okay, we'll see that that's a polar covalent bond as well. Okay, so that being said, we look for these polar covalent bonds, and then we draw these arrows. Okay, why are they important? Well, if you have more than one of these in an atom, then the entire molecule may or may not have polarity. So let's talk about polarity in a molecule. Okay, in the case of something like a methane right here, or any alkane, remember an alkane is sp2 3 hybridized. This alkane has 4 non-polar bonds. So the molecule has a net 0 polarity. We added up all of those non-polar bonds, which is 0, 0, 0, 0, and we equal a non-polar. Now let's do that carbon with a fluorine on it with these hydrogens here. Okay. So each of these carbon hydrogen bonds are non-polar. There's no arrow here. Sorry. There's no arrow here. There's no arrow here. There's no arrow here. But we do have an arrow in this direction here. So if we add up 0, 0, 0 plus that one arrow, is our molecule non-polar or polar? It's polar because if we add up 0, 0, and 0, we have a net dipole in one direction. One of those bonds is in one direction. So we have a polar molecule. All right, let's do something different. Let's do carbon with oxygen, and they're 2 apart. So they're going to have polar bonds where the carbon is going to be partially positive. And the oxygens are closer to fluorine, so they're partially negative. So they're going to be pulling electron density here. So we have 2 dipoles in our compound. First of all, what's the hybridization on the carbon? sp. sp. It's linear.
Oh, carbon dioxide.
Yeah, sorry, carbon dioxide right here. We're talking about carbon dioxide now. That carbon has 2 polar bonds on it and it's sp hybridized, right? So what direction are those arrows going in? 180 degrees, right? They cancel each other out. So that makes this, even though it has two polar bonds, a nonpolar molecule. Okay, let's do one more. Let's do a carbon with a fluorine, chlorine, and a hydrogen and a hydrogen. Okay. So let's see, the fluorine is going to have a dipole moment going in this direction. And the chlorine is going to have a dipole moment, this polar bond going in that direction. And the two hydrogen bonds don't have any polarity at all, right? And the fluorine's probably going to be a little bit bigger because it's going to have a slightly higher electronegativity because it's above chlorine, right? Fluorine's the highest. So that means that we have to add those two arrows together. So if we look at this arrow here, it has a component goes that way and that way. If we look at this arrow, it's a vector that has a component going that way and that way. Okay. So what we're going to do is we're going to cancel the ones out that are going in the same equal and opposite directions and add the two together that are going in the direction not that way. So that means our dipole moment, our polar part of our molecule, is actually going in this direction here because we added all of the polar bonds together to give us the net molecular direction, the molecular polarity. And we call that the dipole moment. So sorry, that's buried here in the thing. It's called dipole, D-I-P-O-L-E moment. And it's measured in a unit called debye. Okay. So the higher the dipole moment, the more polar the molecule is. The more polar groups you have going in the same direction, the more polar the molecule is. Okay? Questions on that? Yes.
If fluorine has the most electronegativity with hitting the dipole, how is it doing that if the hydrogen's already bonded? What is it for?
Okay, so remember, the bond that we're talking about is the electron the carbon gave, the valence electron for carbon and the valence electron from fluorine. We're sharing those two electrons to make our sigma bond. So basically, it's basically pulling both of those electrons a little closer to fluorine. Okay, they're still making a sigma bond. They're still in between the carbon and the fluorine, but they're slightly closer to the fluorine. Does that make sense? That's a great question, actually. How do we know what about the electrons? Do the electrons with the hydrogen bonds play a role or only the bonds? It's only the two electrons that are between the atom, the two atoms we're talking about, because the sigma bond is the one that we're talking about, whether it's polar or not. Okay? Good question. That actually probably helps a lot of people. All right, so we have polar and nonpolar bonds, and we have polar and nonpolar compounds. Okay, so or molecules. So you just make sure you have polar bonds. If you do, then you have to figure out, do they add together or kind of cancel each other out? That tells you whether your molecule has polarity or not. All right, questions on that again? All right, so when we think about this, this is going to tell us a lot about, number one, what kind of compounds dissolve in other compounds. It's going to give us our intermolecular interaction, reactions between two molecules, intermolecular interaction. And it all starts with that, looking at the electronegativity difference, okay? And again, knowing that, your basic electronegativity trend is here, knowing which ones are kind of close together. So like these right here are almost forming non-polar bonds together, but anything else, those are going to be polar bonds. These are non-polar bonds. This is a polar bond. Carbon sulfur is a polar bond. Carbon oxygen is a polar bond, etc. So looking at that relationship, knowing that it's more than one atom away, is typically going to give you a polar compound. Okay, so we're going to use those electronegativity differences. If you want to memorize a number, memorize carbon, oxygen, nitrogen, fluorine, and hydrogen. And then you can compare those to the ones below it. Okay, all right. Now, So we look at which bonds are polar. Then we look at the molecular geometry. Okay, molecular geometry. So basically lone pairs are not going to contribute as much to that as the polar bonds. So we're going to look at that lone pairs separately. But we're going to look at that molecular geometry. And we have to decide whether they're going to be, if you have two of them going like this direction, okay, that means the component that's going toward each other, the components that are going toward each other are going to cancel each other out. But the two components going up are going to add together. So we have to figure out which direction they're going. Once we figure that out, we can say, oh, okay, this one's a 0, this one's a 0, this one's a 0, this one's going in this direction. And that gives us our dipole moment. And if we can imagine that we have a bond between chlorine and carbon. Chlorine is below fluorine, so it's going to be more electronegative. So the positive side is going to be on the carbon, the negative side is going to be on the chlorine. And it's going to pull it in this direction here, shown here. Now, if we were to kind of imagine what it would be like on the outside of that molecule, you're coming in to look at that molecule and you're saying, oh, where are the electrons, right? Electrons repulse other electrons, right? So you want to look for where a lot of electrons are and where not many electrons are, okay? So what we're going to see is in certain zones, right here, we're going to see more electron density than in other places. And whenever we use these electrostatic charts, blue typically indicates partially positive and red indicates partially negative. Okay, meaning there's more electrons in those red and orange zones than there are in those blue zones. Ooh, why is this important? If I wanted to have this molecule come and sit close to another molecule just like it, do I want to put the two negative sides together, or do I want to try to have the negative and the positive side together? Right, because there's going to be less electron repulsion between this zone and this zone than two of the negative zones or two of the positive. That gives us solvent polarity. That's why polar things want to dissolve in polar things, because they have a negative or a partially negative and a partially positive side that they can be attracted to without having as much electron repulsion. Okay, questions on that? Okay, so this interaction between molecules, looking at where the electrons are, is going to tell us something about how their physical properties will change. Okay, so now we're going to talk about physical properties and physical property changes. And I'm going to draw an example from that cis-trans isomerization we saw in those sp2 hybridized compounds, specifically the sp2 hybridized compounds where we had a double bond between two carbons. Okay, we saw that when we went from our carbon with our sp3 hybridization right here, that there is no barrier to having this axis rotate. That sigma bond can rotate, and that freely does. There's nothing that keeps it from rotating. But as soon as we put a double bond there, we saw that those p orbitals had to line up together, and therefore we stopped the rotation. We locked it in place. So when we lock it in place like that, what ends up happening is we end up getting isomerization. So we have a compound that no longer can rotate, and therefore we have to look to see whether it's polar or not. So we have two possible isomers. We have this one right here and this one right here. And this one is called the what isomer? The trans isomer, because if we draw a line here, they're on opposite sides of that double bond, so that makes them the trans isomer. You notice I repeat a lot of things, so hopefully it's the fourth or fifth time you'll write it down. But no, and the other one's the cis isomer here, same side, if we draw that imaginary line. Okay, so now we noted it won't rotate because of hybridization, but how does that affect properties? Well, let's go to bond polarity now. Where are our polar bonds? So if we look at our polar bonds here, the carbon hydrogen bonds aren't polar, but the carbon chlorines are. And the chlorines are more electronegative than carbon, so our positive side is going to be on the carbon side of the bond. Chlorine is more electronegative than carbon, so our carbon is going to be on the positive side of that bond. So let's do that over here. So the chlorine and the chlorine again is going to be on the arrow side of those. So now let's look at those bonds. The carbon-carbon bond is nonpolar and the carbon-hydrogen bond is nonpolar. So we're only worried about those chlorine-carbon bonds. These cancel each other out. Okay, meaning that they have a net 0 polarity or 0 dipole, 0 dipole. Okay, now over here we have the up components that add together, but the two out components are equal and opposite of each other. So those cancel out, but we still have a net dipole in this direction. Okay, do we see how those two little components that are facing out cancel each other out, and only the up arrows add together? So we have a net dipole, and in this case, we have a net dipole of 1.9 dibies. Okay, meaning this compound, the cis isomer, is a polar compound. The trans isomer is a non-polar compound, even though they both have polar bonds and the same number of polar bonds. Okay, and what class of hydrocarbon is this? Alkene, because it has at least one double bond and it's trigonal planar and it has 3 sigma bonds. So all of those things can tell you it's an alkene. All right, questions on physical property? Well, actually, I haven't even talked about physical of polarity, bond polarity versus compound polarity. Okay, now let's look at how it changes the physical properties. In the case of melting point and boiling point, there's 3 things that drive melting point and boiling point: molecular weight, intramolecular interactions, and impurities. But okay, so molecular weight is the #1 driver. As you just add molecular weight, it's going to continue to go up. Okay, as you add polarity or stronger bonds between molecules, it is going to go up. Okay, so in the case of the non-polar compound, we don't have a very strong interaction from molecule to molecule. They both have the same amount of electrons repelling each other. In the case of the cis isomer, which has the dipole moment, we have a positive and negative side. So the positives are going to line up with the negative and positive and negative, and they're going to have a slight more attraction to each other than just the non-polar one. And what does that do? It changes the property. The cis isomer here, let me change colors. The cis isomer here melts at -80 degrees. Okay, but it boils at 60 degrees. So let's talk about melting point. Melting point is where you go from a solid to a liquid, right? So if you go from a solid to a liquid, you want them to be, and it melts low, it means it's going to want to be in its liquid form, right? So it's going to melt, it's going to go in its liquid form, and then when it boils, you're going from its liquid form to breaking all those molecular bonds to giving into the vapor phase, right? So in the case of this, you have a low melting solid because it's small molecular weight, but it boils at 60 degrees because it has to break all of those polar bonds between each of the molecules. Sorry, the polar interactions between each of the molecules. But let's look at the trans. We have non-polar here. It melts a little bit higher. Interesting. But it boils lower. It has fewer intermolecular bonds to break to boil because it doesn't have that polar interaction. So it changes the physical property. Does that make sense? The more interactions you have between molecules, or the stronger that interaction is, the higher the melting point and boiling point. Okay, so we have bond polarity, we have molecular polarity, which gives us dipole moment, okay, and how that affects physical properties. All right, so let's see, we're here at plenty of time. So let's talk about how we can change bond polarity, how we can change the interactions by adding a few more atoms into our system. We started with our hydrocarbons, alkanes, alkenes, and alkynes. The only difference is hybridization on carbon and the number of double bonds we have. And in the case of functional groups, we're going to start sprinkling in other atoms, and the bigger the difference in electronegativity, the more polar they're going to be, and we can have different interactions. So the first thing we want to talk about is the concept of functional group. Basically, it's the thing that does the chemistry, okay? So if something's going to change, that's probably the functional group. Okay, so it's an atom or group of atoms with characteristic properties like carbon-oxygen bond, carbon-halogen bond. The halogen is the functional group. The oxygen is the functional group. It's something other than the hydrocarbon. Okay, it tends to be the reactive part of the molecule, not only where you do reactions, but it also tends to be the part where you have increased or decreased the polarity. And therefore, that's the side that's going to be either partially positive or partially negative. It determines the geometry, the physical properties, reactivity, and the name. Okay, so functional groups are really important. Okay, geometry is controlled by the hybridization plus the number of bonds, right? Because electronic geometry is different than molecular geometry. Make sure that electronic geometry is your hybridization, molecular geometry is your number of bonds. Okay. Physical properties, what kind of bonding it does between molecules, what is its molecular weight, etc. Reactivity, does it react with oxygen? Does it react with hydrogen? Does it react with halogens? You know, what does it react with? And then the name. We know alkanes. Now we're going to get a little more complex and add other functional groups. Most organic compounds have that carbon-carbon bond and have a lot of carbon-hydrogen bonds. So that part is the lower interest part. The part that's different is our functional group, and that's the part we want to play with. And we tend to call these things with hetero atoms. Hetero meaning different than carbon or hydrogen. So anything that has something other than carbon and hydrogen in it has a heteroatom, and therefore it usually has a functional group. Okay, now if we think about our heteroatoms, you know, we're going to see that there's going to be bond polarity with most of them. So that's going to come into play again. All right, questions on that? Questions? Nope. All right. So what are our parts of our functional groups? Okay. Well, most of the time when we see functional groups, we're going to use a generalized form to show you the interesting part. And chemists usually do something like R. R is any alkane, alkene, or alkyne if it's not the part of the chemistry that's working. Okay. So imagine it's just a hydrocarbon, okay? And then whatever the functional group is usually laid out here. So what this is telling us is the functional group is the only interesting part of the molecule. The R can be anything. It can be any hydrocarbon, any alkene, or alkyne, as long as it's not the part that's reacting. The part that's reacting is the functional group, okay? So in the case of our, I'm going to draw this. We have 1, 2, 3. We have 2 bonds between the total of 3 carbons. So this is propane. We'll figure that out soon. But it's also C, 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 hydrogen, 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 hydrogen. See, this is why we draw the little stick figures, because it's a lot easier to draw. Okay, so what do we see here? First of all, we have sp3 hybridized carbons. They're each tetrahedral and they have no pi bonds, no so it's not an alkyne or an alkane. I mean, sorry, it's not an alkene or an alkyne, but it is an alkane. It has no polar groups. So it only has sigma bonds. It has no polar groups. And it has very low reactivity. In fact, we'll learn that this only does a couple things, including burn. So there's very little, couple things that it doesn't happen. But let's change that. Let's change this little hydrogen to a heteroatom, okay? So in this case here, we're gonna draw that, or if we draw it out, it'll be CH3, CH2, CH2OH. Notice this is the condensed form, okay? I drew the skeletal form and the condensed form so that you can get practice drawing all of them. So what does that mean is that this right here is our functional group because it's something different. So this would be called ROH because the OH is the part that's different. Everything else is an alkane, right? So we can just do R for the alkane and then OH is the functional group we have. Now, what's cool about this? Well, first of all, it has a name because functional group usually changes name. We call these alcohols. Alcohol. Some of you are familiar with the word, but it's actually a whole class of chemical compounds, not just the one. Okay, so the idea here is that the H being substituted by that OH, number one, changes its physical properties. It now boils higher. And it's absorbable by the body and used in many metabolic processes. But it also has a polar group here between the carbon and the oxygen is polar. But guess what? The oxygen with the hydrogen is also polar, right? Oh, and then we also have two lone pairs. One lone pair here and one lone pair here, okay? We have 4 sigma bonds on that. I'm sorry, we have 4 electronic zones on that oxygen and 2 sigma bonds. So what shape is it? Correct, because we have carbon, sigma bond, hydrogen, lone pair, making our oxygen sp3 hybridized, molecular structure bent, and guess what? Those lone pairs can be attracted by slightly positive charges. We have a slightly positive charge on the hydrogen and a slightly positive on here. So is this compound polar or non-polar? Polar, and the functional part of it is that OH part. Okay, so that's the different parts of the functional group, and that's showing you that by just adding that different atom, sticking that oxygen in between that carbon-hydrogen bond changes the name, changes the reactivity, changes the type of polarity, changes the physical properties. So it's important to know all the different names and then be able to imagine what their molecular shapes are. All right, questions on that? So let me go ahead and start with a few of the common R groups we're going to see. The R groups are just the alkane substituents we'll see commonly. And you'll see these written in a couple different ways. I have the name and the condensed structure as well as the line bond drawn. Okay, so in the case of that, we're going to look at these in different ways. So the idea here is that methane really has no line bond drawing by itself because it'd just be a dot. But when it's hooked to something else, it's just the sticking out of something else. Okay, that's what that little squiggle means. It means some bigger molecule. Okay, so if you have a methyl group stuck on a larger molecule, you're going to have that little stick out there. Remember what this stick means. This means that there's a carbon at the end of this. There's a sigma bond between 2 carbons. And since there's only 1 bond there, you assume there's 3 hydrogens for a total of 4 bonds. Okay, so that's why our methyl group is CH3. It's abbreviated ME, not meth. There's no H. It's meth, ME. And so then that's how we draw it on there. But by just adding 1 carbon, it gives us an opportunity to put that bend in the line when we do our stick drawing right here. This carbon's the one that's bound to the large molecule. And this substituent is called the F group, ETH. And the YL tells you it's hooked to a bigger molecule. It's a substituent. So when meth is hooked to a larger molecule, it's methyl, YL. Not YN. YN is alkyne, YL, a substituent. Okay. Now, if we go up 1 with 3, we're calling that propane, which gives us our propyl group. YL again is a substituent, which would give us 3 carbons on that chain hooked to some larger molecule. And then our bigger one here, our last one we're going to talk about is butyl, which again would give us 1, 2, 3, 4 carbons in our line drawing, and that's our butyl. So these are all different substituents we can have on a larger chain. So, or you can have them hooked to a functional group. For example, CH3OH is called, in its common name, methyl alcohol. So we can use that substituent to annotate the type of hydrocarbon, the number of carbons there, and then the functional group as well. All right, questions on that? Okay. Okay, so why do we care? Well, there's a whole bunch of different functional groups, and so we can say that in any set of functional groups, there's going to be either polar or non-polar bonds, right? Okay, so if we look at that, we want to look at kind of what those bonds could be, and so we have carbon can be hooked to, let's see, boron, nitrogen, oxygen, not carbon. Well, yeah, carbon, but not as a functional group. Let's see, nitrogen, all the halogens. Halogens can be signified as an X. That's fluorine, chlorine, iodine, bromine, doesn't matter. All halogens can be an X, or you can have a chlorine or an iodine, whatever. So those are our functional groups, right? That's that Z, that's it. Could be anything. The R is the, whatever that carbon chain is, okay? So the electronegativity of the atom determines the bond polarity and whether or not the bond the polarity goes into the carbon or away from it. So for example, if we have carbon and fluorine, we've already decided that fluorine is more electronegative than carbon, therefore the arrow is going to go in this direction, right? But what if we had carbon and boron? Which direction is that arrow going to go? We're going to have an arrow going one way or the other, but slightly polar. So it's going to go toward the carbon because carbon is further away from fluorine. So even though it's not very polar, it's going to go away from. Carbon is the more electronegative atom. We have to pay attention. Most of the time, we're going to see this right here, where it's nonpolar, the carbon is the less electronegative. But we have several examples in this semester where carbon is going to be the more electronegative atom, and therefore the arrow is going to point toward carbon. So, questions on that? Okay, so in the case here, we can have our R group be anything: alkyl, aryl, alkenyl, alkynyl, doesn't matter. That functional group is what we're going to be usually naming it for. And when we have an aromatic group, when we have that benzene ring, it's usually a substituent, okay? And when we call it a substituent, we call it the phenyl ring, or because it's got the YL. The YL tells you it's a substituent right here. And so we'll have that also occasionally on there, where we'll call it pH and then some functional group, pH, OL, whatever. So occasionally you'll say the pH there. That just means phenyl group. R means anything that's not aromatic. Okay. Great. All right. Questions on that? Okay, so let's get into some different classes. They have different names based on the atoms that you're substituting with. So let's get into those right here. And so the first thing I want to talk about is the simplest, what we call alkyl halides. Okay, alkyl halides just means you substitute at least one hydrogen with a halogen. So that's fluorine, chlorine, bromine, or iodine, or the last one there. And we almost never use the last one. But anyway, so the fluorine, chlorine, and iodine. So if we look at the generalized structure, we see R is whatever the alkane is. And a lot of the times I like to draw the Lewis dot structure in there to show you that number one, it has lone pairs to fill its octet. And that helps you remember that it's also electronegative. And we know we have a bond, a polar bond in this direction here. Okay. So in that case, we have usually when we draw something simple, like this would be methyl bromide right here, the functional group is the halogen. However, halogen does not actually change the name. It just changes the class of compounds, but the name stays whatever the hydrocarbon is. And we'll get into that later in chapter 4. But the halo group, halogen, halo, there are no guns and special ops in this one. Halo group is just any halogen, okay? And it's usually the functional group. It's the first functional group we're gonna play a lot with, okay? Now, if we take that instead and replace instead of with the fluorine, let's go over one atom, go to oxygen. We still have a polar covalent bond. Oxygen has 6 valence electrons. Therefore, it's going to bond twice to form sigma bonds and then have 4 electrons in lone pairs. So I like to draw the lone pairs just to show you it's there. Again, when you're first doing this, draw the lone pairs. It'll help you see what shape the molecule is. Eventually, you can start ignoring them. But right now, draw the lone pairs. It'll help you identify things. And when we look at that, the R group can be anything, alkane, alkenyl, alkanal, alkynyl, or an aromatic ring, PH, OH. And something simple like that would be there. And we call that the hydroxy group. Hydroxy, H for hydrogen, oxy for oxygen, hydroxy group, okay? So, and the class of compounds is typically called the alcohol, but this substituent is the hydroxy group. Okay, so let's take that a little bit different, and instead of having a hydrogen on that oxygen, we're still going to do oxygen, which is one carbon, one over from fluorine, still a polar bond between carbon and oxygen, but instead of having a hydrogen on there, we're going to put another carbon bond. So we have carbon, oxygen, carbon bond. That makes it a little bit different because it changes the polarity right here, because now we have the oxygen pulling in those 2 directions, but we have lone pairs. And if we look at the molecular structure, we have lone pairs, so it's a bent molecule too. But we call this the alkoxy group. ALK for alkyl group, oxy for the oxygen. So alkoxy, alkoxy group. So it's also going to be called the ether class, and we'll get into that. Don't worry about that just yet. By adding nitrogen to our system, the bond gets a little less polar, but we have options here. We can have just 1 carbon bonded to the nitrogen, 2 carbons bonded to the nitrogen, or 3 carbons bonded to the nitrogen. Why? If we look at the periodic table, nitrogen brings 5 valence electrons. It wants a total of 8, so it needs to bond 1, 2, 3 times, leaving a lone pair. So we're going to see it bond up to 3 times. So it can bond 1 time to carbon, 2 times to carbon, or 3 times to carbon, and then hydrogen fills up the others. So we'll see in a general structure here, we have a compound here. What shape, molecular shape, does that nitrogen have? Got a lone pair, it's bonded 4 times. So electronically, it's tetrahedral, but trigonal pyramidal, right. And if we look at that, we can see that here, 1, 2, 3, and then there's this lone pair up here. That's again, the best reason to draw the lone pairs right now. And we call that the amino group. Amine is just a nitrogen and a nitrogen carbon compound, so amino group. Okay, now we can extend that to sulfur. Sulfur is just down from oxygen here. And it's a little bit it's a little more non-polar bond right here, but again, it has lone pairs. So that means it's bent. If you have the lone pair sticking up here, again, great thing to do right here when we're starting. And then we call that the mercapto. Okay, it's a sulfur compound, mercapto. And they have interesting groups as well. But if we were to choose, just like we did with oxygen, take that hydrogen off and make a carbon sulfur carbon bond, we call that a thialkyl thio group. Remember, it was alkoxy before, now it's an alkyl thio group. Thio meaning sulfur. Oops. Okay. Questions on that? Okay. We got about 8 minutes to drive the rest of this home. So let's go ahead and talk about carbons and why you need to pay attention to how many things are attached to them. Okay. Carbon, the nature of the carbon, or the nature of how many things are bonded to it, controls a bunch of things. Number one, it controls intramolecular interactions. If they're more ball-like, they have fewer interactions with others than there. If they're more extended, they have different so we want to pay attention to how many times a carbon is bound to other carbons. Okay, so when we talk about carbons bound to other carbons, we have 4 types. We have a primary, which is also looks like, you know, this primary right here. That's when you have a carbon only bound to one other carbon. Okay. Now, why is this important? Well, we're going to see that in a lot of things. Like right here, this carbon is bound to one other carbon. Okay. Which means it has to have 3 other sigma bonds. And so it usually has 3 hydrogens on it or something else. So those are primary carbons. So that's a primary carbon. This right here is a carbon with 2 carbon bonds. So we call that secondary. So carbon, carbon. Carbon, carbon. Here, that's primary, that's secondary. Okay, so that means it's somewhere in the middle of the chain. It can still be a long chain, it can be a straight chain, but it has 2 carbons bound to it. We call that a secondary. Now, if we go to a tertiary, that means we have a carbon-carbon bond and a carbon-carbon bond. Actually, let me erase that mark there and put that there. So that means you have 3 carbons bonded and usually something else. Let's just put a hydrogen there. So we call that a tertiary. Okay. This will become important for a lot of things. Now think about this as, oh, it's not a straight chain anymore. It's starting to get branched. It's starting to have things hanging off the side. So if we look at this here, this would be our straight chain, and then this would be the thing hanging off the outside of it. That would be the substituent. So you don't have any substituents on these primary and secondary carbons, but now that we have this tertiary carbon, we have a substituent on our main chain. And then of course, 4 quaternary is 4 carbons like this. It's actually the carbon in the middle here that has 4. Okay. So we can easily, readily identify them by looking at just this one right here. Pull that up. And there's 2 ways to look at it. Count the number of carbons that are on it, or if it's a hydrocarbon, just count the number of hydrogens that are on it. Going to be the opposite, right? So this has 3 hydrogens, making it a primary carbon. It only has 1 other carbon, 1 other spec that can fill with the carbon. What's this carbon? How many carbons are attached to it? 1, 2, 3 carbons attached to it. What is it? Tertiary, okay? And that makes that a primary and that a primary. And what's this one now? Tertiary. So it has 1 hydrogen on it, and for a total of 4, 1 minus 4 is equal to 3, tertiary. So if we look at this one right here, we can see this is a primary. What's this one first? A. Secondary. Okay, so being able to readily recognize this actually is a good thing to do, because we have certain things about stability and certain things about reactivity where we want to know whether it's primary, secondary, tertiary, or quaternary. All right, questions on that? Okay, so now that we've identified our carbons as primary, secondary, and tertiary, we now have to identify the hydrogens that are attached to that carbon. And if the hydrogen is attached, if the hydrogen is attached to a carbon that is primary, that makes those hydrogens primary hydrogens. That makes sense, right? If you have a carbon, so that means these hydrogens right here are primary hydrogens because those three hydrogens are attached to a primary carbon. And likewise, secondary is going to be hydrogens attached to a secondary carbon and hydrogens attached to a tertiary carbon. And then hydrogens attached to a quaternary carbon. Wait a minute. Can we have hydrogens attached to a quaternary carbon? No, because there's already 4 bonds. You can't have 5 bonds to carbon. So there are no quaternary hydrogens. There's only primary, secondary, and tertiary. In a tertiary, you have 1 hydrogen. You can only have 1 tertiary hydrogen. In secondaries, you can have 2 tertiary hydrogens. In secondary, you can have 2 secondary hydrogens. In primary, you can have 3 hydrogens. Okay, questions on that?
So the hydrogen is only secondary bonded to the carbon that's bonded to the
It's the hydrogens bonded to the secondary carbon. If the carbon's primary, they're primary hydrogen. If the carbon's secondary, they're secondary hydrogen. If the carbon's tertiary, that's a tertiary hydrogen.
no matter where it's at.
No matter where it's at. It's always what the carbon is bonded to. That's why carbon is the most important to learn, and then that one's next. All right, I got 2 minutes. 2 minutes. Okay, we'll do that next. All right. All right, thank you for coming. Please come back on Wednesday safe. If you get Bobcat Crate, look for the streaming. All right, thank you, people at home. Did everybody get that? Okay, all right. All right, great. Thank you for the comment. All right. Goodbye, have a nice day. I am going to stop sharing and do the stop recording.
Good question about the attendance.
Yeah, hang on. Let me just stop sharing and